All right, so we're going to talk a little bit more about the Clausius-Clapeyron equation, but this is what we call the two-point Clausius-Clapeyron equation. Okay, the two-point Clausius-Clapeyron equation, and we use it for a slightly different reason. It's used to find the vapor pressure at a given temperature, at any temperature, I should say. So you can look up vapor pressures for most substances, but they're usually only given like every 5 degrees, like 20 degrees Celsius, 25 degrees Celsius. But if you wanted to know the vapor pressure in between those 2 points, you can use this two-point Clausius-Clapeyron equation. And let me give it to you. It is ln, and this is another equation that can have various forms that are mathematically equivalent, but on first glance look different. P2 over P1 is equal to negative delta H VAP over R, so basically the same thing, times 1 over T2 minus 1 over T1. All right, now what is P2 and T2 and all that? So P2 is the vapor pressure at temperature 2. I guess I could have done P1 first, and P1 is the vapor pressure at T1. Okay, and then of course we already talked about delta H VAP and R. So I think the easiest way for you to see how this works is to just go through an example. So that's what I'm going to do. So here is our example. Calculate the vapor pressure of water at 37 degrees Celsius. Okay, so calculate vapor pressure of water at 37 degrees Celsius. We can use, this can be for any liquid. It just so happens that water is obviously really common, so I tend to pick water. It just makes things a little bit easier. So I don't know why, but I'm going to rewrite that equation. ln P2 over P1 is equal to negative delta H VAP over R times T2 minus T1. Okay, now we kind of got to think about all of our variables here. We're only given one temperature, but we need 2 temperatures, and we also need 2 pressures. So let's just go ahead and start off with P2, because I think that'll be easier to figure out, because P2 is what we're looking for. We don't know. We do know T2, and that's 37 degrees Celsius. But we can't plug Celsius into here. We got to plug Kelvin in, so that's 310 Kelvin. Let's see. Delta H VAP we know. Well, let's talk about P1. Do we know a P1 at a given temperature? Well, if you remember back to the previous video, we know when water's vapor pressure is equal to 760 torr, because 760 torr is 1 atmosphere. And that's what we call the normal boiling point for water, which is 100 degrees Celsius. So we picked that because we know it. We know the vapor pressure at the boiling point. So we picked the boiling point on purpose because we know the vapor pressure. I think I just repeated myself, but you get the idea. Delta H VAP, that we just look up 40.7 kilojoules per mole. And then R is 8.314 joules per Kelvin times mole. Now, from this point, there's just a couple of tricks about units and solving this with natural logs. but it's really, really not that difficult. But we're going to go walk our way through it just so we're all on the same page. Okay. So let's start off by plugging in numbers. ln of P2, because we don't know P2, over 760 torr is equal to negative 40, or let's try and get everything on one screen here. I'm plugging in the delta H of vaporization, 40.7, but let me point out one thing to you. Notice that this is kilojoules and this is joules. Okay, they have to be in the same unit. It doesn't matter which one you pick, they just have to be the same. I'm just going to do times 10 to the third joules per mole. Okay, that makes the units work out just fine. Over 8.314 joules per Kelvin times moles, all times, whoa, 1 over 310 Kelvin. Oh, and I forgot to write in here, this is 373 Kelvin minus 1 over 373 Kelvin. Okay, so there's everything plugged in. Now let's go through and simplify. What I'm going to do is I'm going to simplify the right and leave the left alone. You'll see why in a second. Let's just think about our units here for a second. So the joules cancel out here. This becomes 1 over Kelvin, so it's really 1 over Kelvin. And here we have 1 over Kelvin, so that cancels out. Moles cancel out. Okay, so we really don't have any units left on the right hand side. So let's go ahead and simplify. I'm just going to copy down the left. You'll see why in a second. ln P2 over 760 torr is equal to, let's see, negative 2.67. So all that stuff simplifies down to negative 2.67. If you have trouble with that, shoot me an email. It's really just simple math. Easy to make a calculator error though, so don't be bashful. So now, if we want to get rid of that natural log, what's the opposite of natural log? Well, the E. So if we do E ln P2 over 760 torr is equal to E to the negative 2.67. Okay, that makes the ln go away. So we have P2 over 760 torr, and just type that into your calculator. Remember, E is a number. Okay, it's like 2.7 something. And we get 0.06925, and then one final simplification step. P2 is equal to 760 torr times 0.06925, and we finally come out with 52.6 torr. Okay, so we can ask ourselves, does this make sense? 52.6 torr. Well, that's way less than 760, which is 1 atmosphere. And let's compare the temperatures. We're looking at 37 here versus 100. 37 is way lower than 100 degrees, so our vapor pressure needs to be way smaller. And this is not a linear, vapor pressure is not a linear relationship with temperature. So even though we're at about a third of the boiling point, it is not linear, okay? So what I mean is we wouldn't expect our vapor pressure to be 1/3 of the vapor pressure at the boiling point. So we have a small vapor pressure on the right order of magnitude, so that all makes sense. And that's enough for the Clausius-Clapeyron equation.